Hello, everyone. Thank you very much for joining us today for our live session. My name is Matthew, and Alexander is helping out with tech support behind the scenes. I'm going to hand this over to Professor Impey, and we'll get started with your live questions. Remember, you can ask those in the chat or send an email to our Gmail address.
Okay, welcome everyone. It's interesting times here. Our first day of class is a week away, and we'll start online, but they claim we're going to go face to face soon after 40,000 undergrads. That could be an adventure. Meanwhile, I'm happy to be inside. We've had about 40 days over 40 degrees for most people who use Celsius. But the floor is open for questions about astronomy.
All right, the very first question is from one of our live participants, Junaid, who would like to know what came first, supermassive black holes or galaxies?
That's a big question that we still don't completely know the answer to. It's an important question too, because now every galaxy has a black hole. We know that in the last 90% of the age of the universe, the black holes and the galaxies have grown together because galaxies grow by slow accretion or by mergers and acquisitions. And when two galaxies merge, their central black holes merge and the masses just combine. So it's clear that black hole and galaxy masses will track each other as they evolve through the universe. But the question of which came first is an important one. Some people think on theoretical grounds that the black holes came first. And that's because there's modeling that suggests that a very first generation of stars in the universe, stars that formed before there were any heavy elements, these are called population 3 stars, could go up to much higher masses than conventional stars in the nearby universe, which max out at about 150 times the mass of the sun. So if early star formation could go up to 200 or 300 times the mass of the sun, then you can get pretty hefty black holes, and these would be excellent seeds for subsequent galaxy formation, dwarf galaxies growing to bigger galaxies. And that would sort of jumpstart you in the business of growing a supermassive black hole, because it's been challenging to explain how you can have a billion solar mass black hole within half a billion years of the Big Bang. That's not long to grow one. So that's various lines of evidence that suggest that the black holes came first. But that's not really convincing. It's not observational evidence. It's evidence based on supposition, based on theory. James Webb Space Telescope may help solve this problem actually by looking to higher redshifts than we can do with the Hubble Space Telescope.
The next question is from one of our live viewers, Snea, who would like to know why can't we travel into the past? And somebody else pointed out that we can sort of travel into the future with general relativity, but is the same thing possible traveling into the past?
We can travel into the past in that the arrow of time unfolds in one direction. At the level of microscopic physics, however, time arrow is reversible. So every microscopic particle interaction that we've seen can be made to naturally go in the opposite time sense. So time seems to have no arrow in that way. So if you want to travel in time, your best bet is to be a subatomic particle. Equally, astronomers get to travel back in time, and the way they do that is with large telescopes. So as we look out in space, the finite speed of light means that we look back in time. So telescopes are literally time machines, and with large telescopes we look back to within 5% of the Big Bang. So in a sense we can time travel with astronomy.
We already have people asking about this, and we seem to get it in every live session these days. So for those of you who are interested in more detail about about white holes and wormholes, check out some of our previous live sessions. But we'll go ahead and I'll have you talk about those. So can you talk about how are wormholes or white holes mathematically possible, and are they real things that
Right.
we've ever seen?
Right. We do get this question quite often. So I'll start with the observational part. There is no evidence for wormholes or white holes. Period. That's a disappointing answer, but that's the way it is. So let me talk about the nature of the possibility. Yes, it is possible in general relativity to conjure up a situation in gravity which amounts to a portal in space-time where possibly energy could emerge from the other side, and that would be a white hole. And in a sense, the portal itself between two remote regions of space-time is a wormhole. So you can conjure up, I mean, with math you can do anything. That's the beautiful thing about math. And the math of general relativity is based on curved space-time. And so from in the math you can conjure up all manner of convoluted space-times and multiply connected space-times and convoluted options of geometry that give you wormholes and white holes. And unfortunately, disappointing as it is, there's many things that are mathematically possible that simply don't happen in the real universe. And at the moment, we think wormholes and white holes are in that category. But partly because it would be hard to see a wormhole and distinguish it from a place where energy was emerging from a event horizon-sized region for other reasons, such as accretion onto a black hole. And wormholes are unlikely in principle just because the universe has generally got very globally flat space-time, and so there's no evidence that disparate parts of the universe are connected to each other.
Thank you very much. The next question, excuse me, is from Olga, who is on with us live. And they would like to know, is there some experiment planned that would be able to test string theory?
That's a good question, because string theory has disappointed many physicists, many people. I mean, the theorists who work on it and the mathematicians who love it appreciate its aesthetic value. It is quite an interesting theory at the level of mathematical physics. But it's not part of the science process and method if it's not testable. And there's been doubt that it is testable. And that's because it talks about a regime that is many orders of magnitude, 15 to 17 orders of magnitude of energy beyond anything we can access with laboratory physics or Large Hadron Collider. So when you're so far away from a testable regime, you're really in a difficult position. And so the simple answer is no, string theory is not proven to be testable. However, there are variations or versions of string theory. String theory is not one thing. That's a sidebar I should mention. It migrated from the 1980s through the 1990s into something called M theory, which is a sort of universe of string theories united by the idea of membranes or multidimensional spacetimes. And there are some interesting connections between these disparate string theories that have made people attracted to it. So you're not really testing one thing. It's a bit of a broad target. In some of the string theories, there's possibilities that meter scale physics, in other words, you don't have to go to the incredibly small scales implied by a one-dimensional string, which is 10 to the minus 33 meters basically, that you might be meter scale physics that would show these multiple dimensions in play. And so there are some tests. There have been tests carried out at a couple of the national labs with very good lab physics capabilities to try and look for this physics going on. And essentially they amount to departures from inverse square law behavior of electric and magnetic forces on meter length scales. Very subtle effects, but they would be implicating the graininess of space-time. These experiments have been built, and some of them are now operational. No results have been claimed, no tests have been published. But there's a subset of string theories where a set of lab experiments are claiming they might be able to test them. But it's pretty slim pickings for a theory that's been around for 30 years pretty much, and which people were excited about. But while the math of string theory has progressed substantially with smart people working on it, the experimental verification of string theory is pretty much stalled.
Thank you very much. The next question is from one of our live viewers, and Nuseba, who would like to know, is the universe expanding at a constant rate or at an increasing rate?
It seems that the universe is accelerating. The expansion is accelerating, and this was a discovery from the mid-1990s, 1995 and 96, when distant supernovae being used as standard light bulbs in the universe. So we think we know what the energy in type 1a supernovae is. Those are the supernovae that occur in binary systems. And knowing what the luminosity is and how bright they appear to be, we can measure the distance. So people were using supernovae to measure distance in the universe, and as they moved out in space and back in time, they saw an unexpected result. They saw that the supernovae were 20 or 30% fainter than would have been expected in a standard universe where dark matter is the main invisible thing slowing down the expansion rate. The fact that they're fainter than expected means somehow that the supernovae were further away than expected, and the only explanation for that was that the expansion has been accelerating in the recent past, the last 4 or 5 billion years. So that was the observation. It was of supernovae and their brightness. The inference was they were larger distances than expected, and the interpretation of that inference was an accelerating expansion. Now, to connect the dots to something we call dark energy is something that has very little meaning because we don't have a physical theory for dark energy. So dark energy was essentially a name. It's just a name we attach to the agent of the vacuum that is somehow causing space to expand at an accelerating rate. So that was a striking result, led to the award of a Nobel Prize some years later. And it's been confirmed multiply by the groups that were competing with each other at the time, by other experiments and observations since. So the accelerating expansion seems to be real. However, the interpretation of that, of what causes it, especially physically, fundamentally, is very unclear. So progress on dark energy has been disappointingly slow, I would say, at the fundamental level of trying to explain it.
The next question we have from both an email from John V and a live question from Elias, and they would both like to know, what is a good telescope for beginner amateur astronomers to start with?
Sure. I'm not going to give you exact model number off the top of my head, but there are the main telescope makers, Celestron and Meade. Those are the big guys, if you like, that sell probably hundreds of thousands of telescopes a year, maybe even 1 million. The base of their range are going to be good starter telescopes. They use high quality optics. Now the optics for telescopes are now made of plastic, not glass, but the quality of the plastic has improved a lot, and the cheaper components and lighter components mean telescopes have got cheaper. So it's one of the good things about amateur astronomy is that the cost to get into the market of a decent telescope is now a couple $100. So $200 or $300 gets you the low end of the range of Meade or Celestron, and those are perfectly decent telescopes. You can then spend more money on different eyepieces of different magnifications. So what I'm talking about is just a telescope with probably one eyepiece, and you could get other eyepieces. If you go up the range a little bit, then you get what are called go-to telescopes, and those are the ones where they have little motor drives, and they're computer controlled over the internet, of course, through an app. And they will, if you align them with making an observation of Polaris and the horizon, they will then point to whatever object you plug in or tap in, and you don't have to know the sky to find your way around. So for people who want it easy like that, that's a big help, although it's good to learn the night sky. Then you're up to $300 or $400. I think you can get $350 will get you a very basic go-to telescope. Then they go up to $500 and more. Sky's the limit, of course, if you want to get bigger glass. So these are modest-sized telescopes, but still pretty good at a dark site. For the size of these telescopes, it's starting to matter where you are as much as the telescope itself, because their optical quality and size of their mirrors are similar. So to get the most out of that telescope that you spend a few $100s on, you essentially want to go outside a city. If you don't live in a dark suburb or beyond city lights, then it'll definitely be worth your while traveling a little bit to get to a dark site. What you will see is dramatically better.
The next question is from an email, and the question, Aishwara would like to know, do electrons really exist, or is it really just a belief that they exist after some data from these experiments? What's the difference between a model and a really existing particle?
Yeah, it sounds like a as a basic question, that's a good question because quantum theory, quantum mechanics has led to a evaporation, if you like, of the idea of a particle. So we cannot think of electrons as tiny little particles like BBs or ping pong balls or marbles or tiny objects like that, hard-edged objects, finite size. First of all, in the theory, in quantum theory, electrons have no size; they have no dimension. Which is a very strange thing, and no experiment has ever detected a finite size. However, when you try and measure the position of any electron, you can never pin it down because it's subject to a wave function in quantum theory. So electrons always have a probability distribution for where they are, and that's an irreducible fact of the quantum theory that describes a microscopic universe. It's not a limitation of our measuring apparatus. It's not a problem of the experimenter. It's the basis of the way the world seems to be. So the simple question of asking where an electron is or how big is it, these are not easy to answer because the answer comes back as a probability in quantum theory. And that's true of any subatomic particle. So in that sense, are electrons real? If an electron is a probability distribution or a probability cloud rather than a particle, does that make it less real? Well, not really, because we can still measure the properties of electrons to within the tolerance of the Heisenberg uncertainty principle, and we can do that reliably. And modern electronics, upon which our lives all depend, is based on quantum mechanics and probability applied to electrons. So it's maybe a little less real seeming than a particle where you can say exactly where it is and it has hard edges, and but it's also the way nature appears to be, which is something physicists have still had to get used to and struggle with sometimes.
Thank you. The next question is from Mom Modi, who would like to know, why is it that Mars looks red from Earth?
So Mars is red for a very obvious geological reason, because there are rusts or iron oxides in the topsoil. So that's very basic geological and mineralogy that says that Mars has a lot of these elements. Now Mars has other rocks that are less different from Earth rocks. Earth rocks are mostly carbonates and silicates. Earth has a lot of sedimentary rocks, of course, because it's a water-covered planet with sedimentation forming the rock deposits. Mars was, in the past, a heavily volcanic world, and it had a thicker atmosphere, but not one with oxygen in it. And so it's got more iron-rich deposits that really stem back from that era of volcanism. So that's why Mars is red, and those particulates, which are sort of pummeled by micrometeorites and turned into dust particles, they cloud the air, and so Mars has a sort of dusty red thin atmosphere as well, and the dust storms of Mars do have a sort of dull red brown color when you see them.
The next question is from one of our live viewers. Rochelle would like to know, are the constellations the same from the space station as we see on Earth?
Yes, from the space station, the change in perspective is not sufficient for constellations to look different. So the modern sky has 110 constellations. There used to be, I think the International Astronomical Union officially sanctions 88 of them. Those are the classic constellations, most of which go back to Greek times, but there are 110 total. And these stars in the constellations are, of course, visible to the naked eye, and most naked eye stars are tens to hundreds and occasionally thousands of light years away. So these stars are very distant. Now they're not all at the same distance in a constellation, but they're all very remote from the Earth. So when you go to the space station, you're literally only going a few hundred miles away, and all of the stars in any constellation are hundreds or thousands of trillions of miles away. So that small jump to Earth orbit is not enough to change your perspective for very distant stars, and so the constellations look the same. They would really only start to look different if you left the solar system by some substantial distance, in fact.
Thank you very much. The next question is kind of related to an earlier one, And Aryan would like to know, how far can we see back into the universe's past?
With optical telescopes, we can see very close to what astronomers call the dark ages, which is the time after the Big Bang when the first stars and galaxies formed. There's a chicken and egg question there as to whether stars and galaxies form contemporaneously or stars form first and then clustered into galaxies. Probably it's the latter. And the time after the Big Bang when that happened is not completely determined. The James Webb Space Telescope will hope to do that, but it's probably about 100 to 150 million years after the Big Bang. So with optical and near-infrared methods, we can look back, 13.8 minus 0.1 or so 13.7 billion light years in a 13.8 billion year universe. That's pretty impressive. But of course, with microwaves, we can look back much further because the microwave background radiation left over from the Big Bang was released to travel freely and so give us this microwave image that we see 400,000 years after the Big Bang. That's a tiny fraction of the age of the universe. We're looking way beyond 99.9% of the age of the universe. And that's really the earliest we can directly see with observation.
Thank you very much. The next question is from Bik Ramjit, who would like to know about dark energy. Is it possible that it is a type of electromagnetic radiation?
Probably not. So we don't know what dark energy is, but there are some things we can probably rule out. And electromagnetic radiation is essentially something we can rule out because the theory of electromagnetic radiation, of course, going back to James Clerk Maxwell in the 1870s, is pretty mature theory, and we know the full span of those radiations from tiny and highly energetic gamma rays to large waves and low energy radiation in radio, part of the spectrum. And it's all a same fundamental phenomenon. So moving electric and magnetic charges create electromagnetic waves that travel at the speed of light. And there's nothing in any of the forms of electromagnetic radiation we've understood in the last century that would give it the attribute of causing space-time to expand faster and faster, which is what dark energy is doing. So we know electromagnetic radiation well, we understand it well, and it can't really tell us about what dark energy seems to be doing. So dark energy is behaving in a very strange way. It's acting like it has negative pressure to cause the accelerating expansion of space-time. So the best people have been able to come up with it. It's some form of vacuum energy. Vacuum energy is something known in physics, and it's property of the vacuum that we can measure in the lab, but nothing in lab physics prepares us for or explains the level of dark energy causing the accelerating expansion of the universe. So once again, the basic physics theory that we've had fails. So we need new physics, basically.
The next question is from Hajar, who's on with us live, who would like to know if you could explain the basic science behind the recent capturing of the image of the black hole.
Yes, the black hole image from last year was made with the Event Horizon Telescope. So we see the image presented typically as this sort of orange image of the event horizon on a black background. This is what we would call in astronomy false color. It's not really an image with orange waves of light because it was not made in light. It was made with microwaves. So the technology that was used to make that image involves interferometry, which is the combination of radiation from different telescopes at well-separated locations, and the wavelength of those observations was millimeter or submillimeter waves. So it's more like a radio image than an optical image. And the technology that allowed it to be achieved was using telescopes that were separated across the surface of the Earth. So you were mimicking, if you like, a telescope that had the aperture of the Earth's size. Didn't have the collecting area, of course, of the Earth's area because the telescopes cover a tiny fraction of that. But in resolution terms, it mimics the Earth's size. And when you look at how sharply an image can be made with a telescope using millimeter waves where the telescope has the size of the Earth, you get incredibly sharp images, sharper than you could get with visible light and similar technologies of interferometry. So this was a very powerful method based on interferometry that let us get the sharpest image at any wavelength that astronomers have ever made, and that was sufficient to resolve the black hole at the center of the galaxy M87.
The next question is from an email. Alex Austin asks, how do scientists confirm the existence of water on other planets thousands or trillions of miles away?
So for exoplanets, there's really only a couple of methods to do it. The best method is reflectance spectroscopy. So when we look at the light from a planet, we're looking at the reflected light from the star that it orbits, and if we make a spectrum of that planet, we can look for absorption features which are characteristic of the atoms or molecules in the atmosphere of that planet. If we did that experiment for the Earth, we would see absorption features of typically of water, of course, because they're quite strong in the visible and especially in the infrared. We'd see absorption features of oxygen and ozone, which would be the telltales that the Earth had life, that microbes had created that oxygen through metabolism. And you do the same logic for an exoplanet. So exoplanet reflectance spectroscopy can show you water vapor in the atmosphere of that planet. Now there's a variation of that technique where you can have the planet backlit by the star, and you look as the planet orbits the star, you measuring the spectrum of the star, of course, and as the planet goes in front of the star, you can look for a little extra absorption as the starlight sort of filters through the atmosphere of the planet. So that backlit configuration gives you another way to measure the atmosphere of an exoplanet, and in the same vein, it will show absorption at wavelengths corresponding to the atoms and molecules in that atmosphere. So that's how we expect to do it. Now, that backlit geometry has been used to see water vapor, but in a hot Jupiter. So it's just steam, it's not water. It's a component of steam in the atmosphere of a very hot and massive exoplanet. We haven't yet done this experiment in either of the ways I described it for an Earth-like exoplanet. Those are hard experiments. They will, however, be done in the next few years. So I think that's something that's coming.
The next question is from Pamela, who would like to know, why is it possible to find the oldest rocks on Earth in Western Australia and in Greenland?
There are a few places on the Earth where if you pick up an average rock in any place that you might live in Europe or the United States or Asia or wherever, the average age of a rock on the Earth's surface is a couple of 100 million years old. I mean, that is something that you actually have to dig up, but not too deep. And that's indicating that the Earth, 4.5 billion years old, is resurfaced quite often. And we know that's true because the Earth is geologically active and there's erosion. And so the average rock on almost any place on the Earth's surface is far younger than the age of the Earth. So you have to go to some very special places to find old rocks, and they're essentially called ancient shield regions, where there has been an intact piece of the very ancient continental shield that dates back to the Hadean era, which the Hadean era is the era from about 4.5 billion years ago when the Earth formed to about 3.8 or 3.9 billion years ago. There's very little of the Earth's surface that's that old. It's like 1% or a couple of percent. So it's only a couple of places where ancient shield rock has been sustained and not been subverted back into the mantle or the crust or eroded away so that it doesn't exist. And there are actually 3 places where you can find it. Western Australia is one, and that's where the very oldest rocks on the Earth have been found. Greenland is another, indeed, and there's a place in South Africa where there's ancient shield. So those are the only three places in the Earth where we can find such old rocks. And people have looked everywhere, so they're pretty sure these are the only places.
Excellent, thank you very much. The next question is from sorry, I've lost my place here. From Gioti, who would like to know, if the sky were as dark as ancient times, is it possible that we would see the Milky Way galaxy in almost all parts of the world?
Oh, absolutely, yes. The Milky Way is, if we didn't have light pollution in the Western world, in developed countries, the Milky Way would be visible to everyone. Everyone would know about it. When I teach a big introductory astronomy class here in Arizona, where kids are from Arizona but all over the U.S., and I ask for a show of hands of how many people have ever seen the Milky Way, these 18 to 20-year-olds, the number is about 10% or less. So it's unusual for millennials or young people, young adults living in the United States to have seen the Milky Way. They would really have had to live in a kind of remote area, beyond a suburb even, because suburbs are almost as bright as cities these days. So yes, before civilization, essentially every human, all the pre-civilization humans, were intimately familiar with the Milky Way. It's a little more impressive in the southern hemisphere because the center of the galaxy rides high overhead in the summer in the southern hemisphere, whereas we don't get to see that central part of the Milky Way directly. But the Milky Way as a band of light across the sky would have been just a spectacular and very familiar sight to ancient humans.
All right, the next question is from Hilda, who would like to know, in your opinion, what consequences could the mixture of robot and human exploration have on future space missions and space exploration?
It's an interesting question because it's a matter of some debate with space scientists and within NASA, of course, and the space agencies, is what is the appropriate balance of human spaceflight and robotic spaceflight. So the simple truth is that for planetary exploration, for example, robots do far better than humans. The distances are so large, and we've obviously only ever been to the moon in 50 or 60 years of the space program, not even to Mars, which is an indication of how hard it is. However, we've sent robotic space probes throughout the solar system to all the planets essentially, and a few probes have now left the solar system. So robotic probes of the solar system and doing quite sophisticated things with rovers and remote sensing is a cheaper way to do it, and it makes it feasible to go a billion miles or more beyond the Earth. So that argument would seem to be open and shut case, that you're better using robots for this kind of work. However, there's a community, and it includes a lot of astronomers too, that think that it's important for us to be out there showing that we can live in space, we can work in space, we can conquer the space environment, if you like, and make parts of beyond Earth regions habitable by us as extensions of humanity. And so I think that will happen too. So it's not in the end going to be an either or. But in terms of science, planetary science, bang for the buck, robots are the way to go for sure. Because the human exploration of the solar system and then beyond is going to take a long time, decades. And beyond the solar system, I'd say centuries.
The next question is from one of our live viewers, Broswell D'Souza, would like to know, is space and time more distorted around a neutron star compared with our star, the sun? We know that there's massive distortion around a black hole, but what about neutron stars?
Yes, definitely. Neutron stars, the gravity of neutron stars is not as intense as black holes, but they're within a factor of a couple of the density of a black hole. The amount of mass density inside a neutron star, pure neutron material, it's essentially like nuclear matter, is not very far away, a couple of orders of magnitude away from the matter density within the event horizon of a black hole. And so yes, the space-time distortions of general relativity apply strongly to neutron stars. In fact, when you look at a neutron star, not that we can make close-up images of them because they're far away and they're very small objects, the size of a small city, when you do the math, it turns out that if you look at a neutron star, you actually can see 2/3 or more of its total surface, as opposed to just half, which is what you'd obviously think. And that's because of the bending of light lets you literally see around behind the neutron star and see more than half of it. So people have made those little models, and it's a very interesting sign of those space-time distortions.
The next question is from Cheeky Bear, who's on with us live, who would like to know, could a volcano on the surface of a planet spew out enough material to form a ring?
That's an interesting question. And really, as far as we know, the answer is no. And that's just because the places where there's volcanism are substantial enough worlds that their gravity would essentially stop the volcanoes from ejecting material into orbit and beyond. So you're essentially asking, the question is, another way of asking the question is to say, can any volcanic world that we know of in the solar system send material to escape velocity? And the answer is no, it can't. So some of them will come a little close. I mean, take supervolcano on the Earth, none of that we've had recently, but like the Toba supervolcano, which is I think 60 or 65,000 years ago. Even that supervolcano, which is probably 100 times the intensity of the Mount Helens explosion of 1980, was not able to eject material into Earth orbit. Mars is a heavily volcanic planet and less mass, but if you do the math, even on Mars, when it was actively volcanic, material would not be ejected. Venus is the most volcanic world in the solar system and about Earth size, but the atmosphere is thick and its gravity is strong, so once again, no way to get the material out to form a ring. Strangely, the world that comes closest to fitting the bill for being able to do this is a tiny world. It's Io, one of the moons of Jupiter. Io is a very small moon of Jupiter that is volcanic and sort of kilo for kilo the most volcanic world in the solar system. And the volcanism there is not due to its mass, obviously, because it's a small moonlet, but it's due to this tidal flexing caused by its parent planet. So that squeezing of Io in its elliptical orbit and the tidal forces have turned it into a sulfur volcano paradise, or hell, depending on how you want to look at it. And those volcanoes, because of the weak gravity of Io, they do send the sulfur, almost pure sulfur, into lazy arcs that rise way above the surface and come actually quite close to escape velocity, but not quite. They fall back down.
The next question is from David McAway. If gravity is a warping of space-time, why is there a need for a gravity particle at all?
And that's a good question. And in a sense, it's a matter of formalism. It's a construct of particle physics. And it's not, so I'll be very direct, it's not necessary that gravity be represented by a particle, actually. So general relativity does not call for a gravity particle, as the question alludes to. General relativity talks about the way that mass and energy bend space and time, where both of those are hyphenated. So mass energy is a hyphenated entity. You can interchange mass and energy. And space-time is hyphenated because space and time are connected through the theory of relativity. And in general relativity, it's not necessary to have a particle called a graviton. So the idea of a gravity particle emerged out of particle physics, where the schema for how the world works has involved various fundamental particles, protons and neutrons, which are of course made of quarks, electrons, muons, neutrinos, etc. And the four forces of nature in the particle physics universe of explaining fundamental physics also are particles that carry and exchange the force at the speed of light. So for the electromagnetic force, obviously it's photons. For the strong force that binds an atomic nucleus, it's gluons. For the weak force, also in the nucleus, it's the W and Z boson particles that are responsible, for example, for radioactivity. And for gravity, by extension, by analogy, it's a graviton, a spin 2 or particle or boson. But a graviton has never been observed. And so it's really analogizing from particle physics that leads to the idea of graviton. It's not required by general relativity. And as we know, one of the limitations of physics is that there's no reconciliation yet between general relativity and quantum theory or particle physics. So it's not clear that when those are finally resolved in a single unified theory, you'll even need a particle called a graviton.
The next question is from Symphonics Co., who's on with us live. Is there any electromagnetic radiation spectral line or spectral feature in the likes of the 21 centimeter hydrogen line that has been discovered by astronomers but whose origins are not yet explained?
No, not that I'm aware of. It's always an interesting question of whether there are any spectral features from cosmic objects that are mysterious and not known. That would be interesting. That, for example, could indicate, a new substance or create an artificially created chemical substance that would indicate some intelligence at work. So people are definitely out on the lookout for unexplained spectral features. But there's been nothing seen, particularly in the radio part of the spectrum, that is fundamental and seen, somewhere else in the universe and routinely in the universe, that has no explanation. The 21 centimeter line is a spin transition of neutral hydrogen, the cold form of hydrogen that's seen in deep space, and that's well understood. The other spectral features that are seen in the radio and sub-millimeter part of the spectrum are typically vibrational or rotational transitions in molecules in star-forming regions. So there are hundreds of different spectral lines that have been seen in, like, the Orion star-forming region and the Taurus star cloud and so on. And these are lines of carbon monoxide, oxygen, carbon dioxide, nitrous oxide, all the various simple molecules that are in the interstellar medium. And they make tons of spectral features throughout the long wavelength spectrum. And they're pretty much all identified. And people have not yet looked at those very complex spectra out of star formation regions and seen lines that they couldn't identify yet.
The next question is from Subham, who would like to know if we can send data or information using gravitational waves.
Not yet, but it would be a fascinating possibility to send gravitational waves to encode information that way. So far, all we've done is observe natural phenomena in gravitational waves, and in particular there are the collisions and mergers of black holes and neutron stars. So, in the theory of general relativity, gravitational waves or gravity waves are produced anytime a mass configuration changes. So anytime you have a variation in mass or its configuration, it doesn't have to change overall mass, it can also just change how it's distributed. Then ripples in space-time go out at the speed of light. So if we were able to manipulate matter sufficiently strongly or robustly, then in principle, yes, we could make gravitational waves. And so it does hold out the possibility or the prospect of a means for coding and generating information, because obviously if we could manipulate matter in a way to make gravitational waves, we could manipulate matter in a way that nature did not. And so those gravitational waves would be telling someone who received them that some civilization or some artificial entity had created these gravitational waves. So it would be a very interesting prospect. We're not close to it. I mean, we may be decades or 100 years away from it. We have no technology to do it. If you reverse the logic, it's interesting too, because it suggests that even though SETI, the Search for Extraterrestrial Intelligence, is focused on pulsed radio signals and pulsed optical signals, such as from a laser, what if an advanced civilization was able to manipulate masses and gravity sufficiently to generate gravity waves and communicate that way? We know they travel at the speed of light, they pass through matter easily, and so the universe is transparent to gravity waves. It's a very good mechanism for communication. So people have already speculated about that.
Naroon Joe, who's on with us live, would like to know, what will the JWST, the James Webb Space Telescope, uncover, and what will it allow astronomers to do?
The James Webb Space Telescope is a much anticipated mission that essentially succeeds the Hubble Space Telescope. Hubble Space Telescope is still operating, but it's a small telescope, 2.4 meter mirror, the biggest that could fit in the shuttle bay, because that's how it was launched. The James Webb is will sit at a Lagrange point, a million miles from the Earth, and will unfold when it gets to its location and unfurl solar panels to power it. And it's a 6.5 meter mirror, so an order of magnitude more light gathering power than Hubble, and working more at longer wavelengths or near infrared and red part of the optical spectrum. It's already 7 months delayed, partly due to the pandemic and partly just due to cost overruns and problems within the project that go back years. It's very much delayed and over budget. but it's almost certain that it will go. And when it goes, it's designed to look for first light in the universe, the era when the first stars and galaxies formed. We think about 100 million years after the Big Bang, so very early, within the first few percent of the age of the universe. It's also very well suited in the infrared to look at the signatures of exoplanets and perhaps sniff out life-altered atmospheres of exoplanets. That's another exciting application of the telescope. And again, by working in the infrared, it's going to be able to look deep into star-forming regions with great light-gathering power and resolution and see just the details of how stars form in these chaotic, dusty, and gassy regions. I'm sure it'll do lots of other things too, because most big projects with diverse capabilities and instruments make discoveries that the builders never anticipated, which is of course why astronomy is fun. A lot of it is still based on unexpected discoveries.
The next question is from Varun, who would like to know, in your lectures on, in some of your lectures, you have discussed patterns and that we can see the golden ratio everywhere in the universe, like in spiral galaxies. Do you have any idea why that is, why we can see this particular pattern all over the universe?
It's not necessarily it's a fascinating aspect that there are certain numerical ratios or progressions that are seen in nature from things as diverse as, the spiral pattern of a flower, the central region of a flower, to chambered nautilus, sea creature, to spiral galaxies. So it's basically a logarithmic spiral where the pitch angle is a certain number and it creates a logarithmic ratio of the segments of the spiral moving outwards. At some level, it's just a natural progression of an object that has no preferred scale. So you can set structure on very many different scales, and the universe, because it operates according to gravity, and gravity is an inverse square law that applies over very large distances, it tends also to have a lot of scale-free structure in it. So in a sense, these numbers that come up in nature are functions of processes that have no preferred scale, and so they play out over all different scales at once, and the relationship between these often has these various fixed numbers. Now in astronomy, the numbers are not as fixed. We don't see Euler's number or the transcendental number E or the transcendental number pi figuring in astronomical structure. So I don't want to get mystical and pretend that that's the case. But we do see certain patterns that just arise from scale-free processes like gravity.
The next question is from one of our live viewers. Gnashawar would like to know, are Uranus and Neptune blue colored due to the presence of water or something else?
The color, and they're very pale color. We kind of get used to seeing false color images from NASA missions, and they turn the volume knob up on the colors way beyond what is true. If you look at a true color images of Uranus and Neptune, which you can do online, so it's worth looking for them to see how much more subtle the colors really are, is the very palest blue, and it's almost gray blue. It's not really oxygen. That a lot of that blueness comes from methane. It comes from carbon dioxide. They're very small concentrations of cyanogen and other heavy element related compounds, which also give a slightly blue tinge. So it comes from a set of trace ingredients as well as from methane in those atmospheres. Even methane is a trace ingredient. The dominant gases, hydrogen and helium, of course, because these are gas giant planets, they don't have a color in their reflection spectra.
The next question is from Sayak, who sent us an email. Are there any phenomena in space that are like tornadoes or vortices that can act like black holes to sort of suck in and grab material in space?
That's an interesting question. So black holes, of course, have that capability. They're sucking in matter, and they have rotation, so they do have the nature of a vortex. And what that turns into is an accretion disk around black holes, which is a commonly observed phenomena. They radiate in X-rays because that gas, as it's getting towards the funneling in region of the black hole, is heated up to temperatures of millions of Kelvin. Other than that, of course, there are, the only thing that approximates a vortex in the universe other than a black hole is perhaps a spiral galaxy itself, which has angular momentum. But these galaxies are rotationally supported and held together, of course, by dark matter. So there's no net large-scale transfer of mass to the center of a spiral galaxy, such that you would compare it to a vortex. So I think black holes and compact objects like black holes and neutron stars are the only places that, have that kind of vortex capacity.
The next question is from one of our live participants who would like to know, is it possible that huge gravitational waves could affect the path of spacecraft or affect spacecraft in any way?
So gravitational waves are, they're not really impeded by objects or mass at all. I mean, when the gravitational waves that were detected in 2015 and 2016 and beyond by LIGO passed through the Earth, they affected the Earth almost not at all. And so that's true of what happens in space too. So for a spacecraft or a person, gravity waves passing through really have essentially no impact at all, because remember, the gravity waves that we've detected so far, originating, a billion or more light years away in space, of course, from long gone objects, displace space-time, distort space-time by a distance much smaller than the size of a proton. So these are so subtle that even a more cataclysmic gravitational wave, imagine a gravitational wave not from two solar mass black holes colliding, but 2 billion solar mass black holes colliding, like at the center of a galaxy. Even those gravitational waves, the displacement of them would be a tiny fraction of the size of an atom. So again, imperceptible to anyone in space or traveling through space.
Excellent. Thank you very much. The next question is from one of our live viewers, and they say that some Indian scientists have disproved that, or claimed to have disproved that black holes exist. But what do you know about this, and what is the evidence that we have for black holes existing anywhere, but in particular at the center of our galaxy?
Yeah, I'm not aware of that particular study, but I'm aware of the studies that argue for the existence of black holes and their reliability. And I would say, especially when it regards the black hole at the center of our galaxy, the evidence for that black hole is better than any other black hole in the universe, including all the dead star black holes that were the original black holes to be discovered, Cygnus X1 in 1969, for example. And the reason is we've now tracked the orbits of dozens of stars around the center of our galaxy, close in, within few light days of the nucleus. And each of those orbits is a probe of the central mass, and each of them speaks to the density of the central mass causing those stars to move. And they're moving very fast. Some of these stars in that central region are moving 1,000,000 miles per hour. So, by Kepler's laws, because you don't need general relativity unless you're close to the event horizon, you have a very robust measurement of the mass of the center of our galaxy, not just from one star, but from each of the stars orbiting it, and each of the stars gives the same number, and that number is around 4 million times the mass of the sun, and the region of space within which that 4 million solar masses is concentrated is such that only a black hole can explain it. So I think really, I'm a scientist, so I like to be skeptical and suitably skeptical about conclusions, but in this case, the evidence for the black hole in the center of our galaxy is extremely compelling.
Excellent. All right, the next question is from one of our live viewers who would like to know, I'm sorry. Do you think that the James Webb Space Telescope will really see inflation, and what will they be looking for? What evidence will they be looking for to prove inflation?
I think the James Webb Space Telescope is not going to have any great handle on the idea of inflation, which is the very early exponential expansion of the universe to far beyond the horizon size, meaning that the universe as a whole is much bigger than the observable universe we see. There are no obvious experiments with James Webb, which is really just an extension of a telescope like the Hubble Space Telescope and its capability, that address inflation. The best next handle on inflation is going to come from an experiment that kind of released a false result a few years ago, the BICEP 2 experiment in the Antarctic. And that's using microwave background observation. So microwave background radiation left over from the Big Bang, if inflation is correct, should have imprinted on it a particular polarization signature. So the microwaves are polarized. They have preferred electrical direction of their vectors. And that signature is characteristic of inflation. And you have to work the models to see what the signature should be. It's an extremely subtle effect because it's a fraction of a percent of polarization, and polarization itself is a fraction of the intensity signal. So these are experiments that have to be have a precision of a few parts in 10 million to see the inflation signature. And the one that published a few years ago sort of got it wrong, because the signal they saw was due to dust in our galaxy and not due to something in the early universe. But those experiments are going to keep going and get better and better as we have more microwave telescopes in the Atacama Desert and also in the Antarctic Plateau. So I think those will be the experiments that potentially can tell us that inflation really did happen.
The last question for today, so it's 10:59, so we're going to have to wrap up our session. So the last question for today is from Mr. Marble, who would like to know, what is the physical size limitation of a telescope?
That's an interesting question, and depends on, of course, what wavelength you're talking about. The largest telescope of any kind, of course, are radio telescopes, and the largest single dishes so far was the Effelsberg 100-meter telescope in Germany. So we've not made radio telescopes that steer and move bigger than 100 meters. Obviously, the Arecibo dish is 305 meters across, but it doesn't move. It's sitting in a natural hollow in Puerto Rico. And the physical size limitation for radio telescopes, the Chinese now have a slightly bigger radio telescope. For a single dish radio telescope, you could probably go up to several kilometers if you find the right place where you could support that structure without too much problem. So we can go bigger with radio telescopes. With optical telescopes, it gets very expensive to get much bigger. So the telescopes that are currently being built of the next generation are the 30-meter telescope by the University of California and Caltech, possibly to go to Mauna Kea if they resolve their issues there, and our Giant Magellan telescope, which is effectively a 22.5-meter telescope in Chile, and the Europeans' extremely large telescope, which is a roughly 40-meter telescope made from mosaic. People have done engineering studies, and in fact the Europeans were originally looking at a 100-meter optical telescope. So they actually went through the engineering studies of 100 meters, and that was doable, but that was pretty much at the hairy edge. The engineering got extremely difficult after 100 meters. And the enemy really at this point is just gravity. It's just really hard to make a big mechanical structure in the Earth's gravity and make it move accurately and nimbly on the sky, much bigger than 100 meters. Now, if you had the infrastructure to do such an experiment on the moon, or in Earth orbit, if you could assemble telescopes in Earth orbit, you could potentially make them bigger than 100 meters. But on the ground, I'd say a few kilometers is the radio limit, and 100 meters is the optical limit. So thank you very much again for all your questions. Thanks to Matthew for facilitating, Alexander for being an invisible electronic guru behind the scenes, and we'll announce our next few sessions soon and be with you next week. Okay, goodbye.